In today's video, we will be exploring what happens to absolute signals between small diameter through-wall holes and much larger through-wall catastrophic holes. I recently made a video showing the effect on differential signals, but it'll be interesting to see what happens on the absolutes. So what we're going to do is take this 9010 copper nickel tube sample, which has the 420s, similar to an ASME standard on one end, a 60% flat bottom hole right here, and then a 0.052 inch through-wall hole. And then what I did is I made the drill bit a little bit bigger, and I did shallow OD pit-like indication. Then I got a little deeper, then I drilled a through-wall hole. I got a bigger drill bit, did the same thing. I got a bigger drill bit, did the same thing. And then I got even a bigger drill bit and made these series of holes and got that one. Then I went to the biggest drill bit I had and I made one hole. Then I believe it was 2 holes, and then I went to 3 holes. So there's a lot of metal missing there. You can imagine what that's going to do to the amplitude of our signals, because the amplitude of signals is a product of the length, width, and depth of a discontinuity. And if you take the length, width, and depth, you will have the volume. So the more metal that's missing, here there's lots of metal missing, you're going to get a very large signal. We're also going to look at what that does to your phase today. So let's just acquire the data on this standard. I'm going to end up pushing the probe through and out this end. And then when I start recording data, this will be the first data you see, so it'll be in the bottom of your strip chart. And then when this probe comes through all the way to this end and exits right here, that's going to be the latest in time data, or the data that you see on the top of the strip chart. So let's go ahead and hit acquire. I'm going to insert the CoreStar barnacle scraper bobbin coil probe, which is capable of collecting data from the differential and absolute arrangements. I'm going to null the tester inside of good metal, push the probe out, and then I'm going to steadily pull the probe back through the cal tube. All right. So if we look at our strip chart, obviously I have a differential on the left. That's why the indications go 2 directions. And on the right, I have channel 6 absolute. So the flaw indications only go in the positive direction. So let me zoom in on that a little bit. So you can get a little more clear picture of what we're dealing with. All right, so what I did in the beginning was I went and looked at the first three flaws were on the left-hand side of that standard, which is right here. And then if we go over, I have 4 different frequencies on my screen here. So the green is 90 kilohertz, and then the red is 90 kilohertz absolute. The purple is 45 kilohertz differential, and then 4 is 45 kilohertz absolute. So you can see how the different frequencies, rotated counterclockwise with decreasing frequency on the OD flaws. That's how they act. Then, of course, the next flaw we had was the 60%er. The 60%er, which is right there. 90 kilohertz, 45. You can see how it rotated counterclockwise, decreasing frequency, same thing with the absolutes. And then next we're going to go up to the 100% hole. So what I did was I set noise horizontal on the absolutes, and I set the through wall 0.052 inch hole to 40 degrees on the differentials. So then what we're going to get into is this first small OD pit with the slightly larger drill bit. And that's going to be, what I have to do is turn up my span a little bit. Okay, so that is the beginning of the small OD pits. There's 4 of them in there. And then you've got the hole, which is right there. Okay, now I set the 0.052 inch hole to 40 degrees. But if I go into measure and hit peak to peak, that's at 39 degrees. So somebody will say, it's the same, right? Well, let's see what happens when we go to a slightly larger hole. Okay, let's go to here. Do the cursor. It's an older tester, so I'm using the hula button instead of a mouse. So there we're going through the next series of OD pits right here, leading up to the significantly larger hole. So these are your OD flaws. And there's your next big hole right there. So because the signal is getting much larger in amplitude, I have to adjust my span to get it on the screen. So your little OD flaws are, only like 1 division here, whereas the through-wall hole is much larger in amplitude. But hey, what happened to the phase on that one? Looks like it dropped a little bit, right? Let's go measure it and see. Peak to peak, 32 degrees. See how that dropped? So yesterday we were talking about the weighted average and how that works. Eddy current density is most dense at the ID surface of this tube with a bobbin coil. And because the eddy current density is strongest at the tube inside surface, the eddy currents that are disturbed at the ID surface are going to have more input into the phase and amplitude of the signal. They're going to provide much more input or weight than the much less dense eddy currents deeper in the material will provide towards the phase and amplitude. Okay, then we're going to go up to the next series of holes right there. Those are these guys leading up to a much larger hole. There it is. What happens if you do a peak to peak on that guy? Now we're down to 26 degrees. See, it's dropping every time. That's because as the diameter expands, there's more eddy currents disturbed. Not only at the OD surface of the tube, but the ID surface of the tube. And since the eddy currents are densest at the ID surface, that's going to pull your phase down. And then we get into the real scary part of the cal tube, which is like a bigger hole and then 2 holes, then 3 holes. So we'll see what happens there. And I have to span down so much to get this last hole on the screen that the 4 or 5 small ODs that I have leading up to the next big hole are very small here. See that? There's like 4 or 5 different flaws in that area. If you don't believe me, I could change the span a little bit, make it a little hotter. And now you can see the holes in that region. If you wanted to see them on the strip chart, I would have to go to the strip chart and make the span a little hotter. Now you can clearly see those smaller flaws on the strip chart. But so now I'm going to go up to the next. There's the big hole right there. I'm going to have to zoom in a little bit because now the strip chart's starting to get really busy. Now the last 3 you see here are identical to what were on the left end of the standard, where I got the 420s, the 60, and the 100. But right in here is where I've got all those big holes. So I'm going to go there, and I'm going to make my window size a little bit smaller so we can zone in on that first big hole, which is right there. And then I'm going to change my span such that we can get it on screen a little bit better. Then I'll go over to, we'll just put channel 3 up, 4, 3. We'll bring that one down a tad. We'll go to, let's see, we'll go to 5. We'll bring that one down a little bit. And we'll just measure and see what we got now. Now we're down, not 202, so I don't have my window small enough. You gotta be patient. Make our window a little smaller, so we're not getting a bunch of extra razzmatazz in there. Peak to peak, 21 degrees on 90 kilohertz. 19 degrees, 145. 207. That just shows you that I didn't set the rotation on channel 5 correctly to begin with. If I did, it would look something more like that. Now that's 19 degrees. It would probably be more like about that. So 21, 19, 16 degrees. Just to make sure I didn't lose my mind, let's go look at the 100% hole with the new rotation here. And that's going to be right there. There's your signal. Look at that. What's that? Looks like about 35. Measure peak to peak, 32 degrees. All right. So just to keep me honest, we'll put that up to 40. And then we'll go back to that first really big one here. Now, these are all blowing off screen here, right? And it looks like the blue data is channel 4, which I'll put all differentials up here since we're in that sort of mode right now. And then we'll hit measure peak to peak, 21, 19, 24, 230. I got that one upside down too. I wasn't really focusing on that when I was doing this setup. So if you bring that one around to where it should be. Now that's a pretty low frequency for this config. So it's not something that we would normally use for flaw detection. But now that I manipulated that, of course I'm going to want to go back up to my 100 to see where that one comes in at. And gotta make the span. Notice how hot I have to make my span with the low frequency, just to get this signal a little bit bigger. But so now if I bring it here, what does that give us? Measure peak to peak, 35. We're going to bring that rotation up just a tad because we're going to have them all at 40. All right. Now, when I go back to my cursor and get on that big 100, they're all blowing off screen, but that's pretty much what the angle's going to be. Let's just do a peak to peak and see what we get. 21, 19, 24, and 30 degrees. So they're all significantly lower than they were on the much smaller diameter, 100% pit. So then what happens when I go from one huge hole to two huge holes? The money is on what? That the phase drops? I'm going to say the phase is going to drop. So let's go measure this one and just kind of remember what it is. No, that's not right, Eduardo. Let's go here. See if that does it for us. Measure peak to peak, 21, 19, 24, 20. So 21, 19, 24. 21, 19, 24. 21, 19, 24. 21, 19. And now this is the next one. 21, 19, 24. That's not quite right. That's going to be the one right there. So 21, 19, 24 is what we had before. Peak to peak. 19, 16, 21. See how it dropped even more? Now we're going to go, let's see, so that was 2. Now we're going to go to 3 holes. 1, 2. 1, 2. Yeah, there's 3 holes here. So 19 degrees, 16 degrees, 21. 19, 16, 21. 19, 16, 21. And there's the next transition. So 19, 16, 21. 19, 16, 21. 18, 18, 23. So that's kind of getting into the area where maybe they're not going to be dropping so much again. But for a while there, they were definitely dropping. Okay, so now we're going to go to peak again. 9, 22, and 18. Looks like for the next one they dropped a little bit. But keep in mind that I don't have these things drilled in a precision manner like they would be in a machine shop. You know, they're offset a little bit. Axially, they're offset. The inclination of my drill could have been, you know, normal or perpendicular to the tube on one. It might have been a degree or two off on the other. So that's going to make my phases act a little bit wonky. Now, what happens when we go to this very last one where I basically mangled the tube? That's going to be this last one up here. Now, if you look at the strip chart, and actually, let me go and change the span of that left-hand strip chart just a tad to bring the signals on screen a little bit more. Okay, that's maxed out. And I'll do the same on our absolute strip chart. Strip charts are a measure of distance or time. Okay, and if you look at this last one, last two really, where I've got some axial spacing in between the holes, you can see that, especially on the last one there, that the distance from the beginning of that flaw series to the end is wider or took longer. That's because there's a bigger, the damaged area is a little bit longer than the damaged area from the preceding set of flaws. And again, depending on the configuration of the hole or holes that I made, it's going to slightly change the phase and amplitude of the signals. Now, you're not always going to find flaws like this in real tubes, but there are, you know, times when tubes blow out, you get big gashes, foreign object damage, tube severs, all sorts of crazy stuff like that. So here, let me try to manipulate my cursor a little bit and see what we got going on there. So that's a really big one. I'm going to make my window size a little bit bigger. So capture the whole signal. Measure. Goes a lot faster with a mouse, but I don't have a mouse here. Okay. That's an ugly looking signal there, let me tell you. Okay. Let me crank down the span a little bit here. A little bit more. I'm looking at the green data right now. Whoa, it's starting to saturate. You see that right here? See where it starts to square off? That's because my holes are getting too big and the system can't handle it. So, you guys want to see the effect on changing our preamp gains? Before we do that, let's go see what some of the absolute channels are doing on these huge signals. Let me go over here, channel 4. Let me hit null. Ooh, oh, look at that. That's 90 kilohertz on the absolute. It's blowing right out of the water. See, it's saturated. So let's go back to our hardware config. And we will try. No, I'm just experimenting with this. I don't claim to be an expert at all things eddy current, but I am learning along the way. I'm just cranking this down to 40, and we're going to see if that makes a difference on the absolutes. And actually, remember how some of the differentials were starting to saturate? I'm just going to crank these down a little bit. The manual, Zetec owner's manual for the MIZ-27, says if you use the gain of 34, you won't saturate. But we're trying 40 for right now because we can. So now I'm going to go and put my barnacle scraper probe back in the tube. I'm going to null to change my gain settings. I'm going to pull the probe back through the standard. Okay, now let's see where we're at. Wow, the strip charts look a little bit less busy because my signals are smaller, right? So now I got channel 1. What I still need to do, though, is make the strip chart a little bigger. Because remember, this is where all the big flaws were at the end. That's the, grab my standard again. That's where all these big holes are at on the right-hand side of the standard. So that was a big single hole. There we go. That was the big single hole right there. Let me crank the window size down a little bit. Hey, you got to be patient with me. You know, there's a lot of jumping around here to teach all these lessons. Okay, there you go. No. And you're like, come on, Ed, what about all the other signals that are not looking very pretty on the screen right now? Well, all you have to do is ask, and then we just go and bring them all on screen a little bit here. See, it's just an adjustment, a couple adjustments. You have to be patient when you're doing eddy current to get your setups just exactly right. So when you make calls and enter a report and give them to the customer and hand them a bill, that your results are accurate and repeatable. And one of the parts of making your results accurate and repeatable is to use an ETSS, or an examination technique specification sheet, that has all the essential variables of your test captured like in a report. So next time you come and do a test, you can use the exact same equipment, cables, probes, settings, and analysis technique to make sure that you're going to have, you know, dependable results. Because engineers are going to take those results and they're going to dump them into an Excel spreadsheet, and then they're going to start trending the numbers. And if they're trying to trend numbers and make sense of growth rates, when you were using different test parameters from year to year, it's not going to make any sense. And they're probably going to end up either spending a bunch of money taking material out of service that is perfectly fine, or you could also do the opposite and have false negatives, which are you got stuff that's really bad in the material, but you don't catch it because you're test sensitive or your test technique is not set up right. All right, so now that we have our spans pretty good here, we're just going to go and put a little size on these and see where we're at. Remember, the 0.052 inch hole was 40 degrees, and then here we got 20, 18, 23, and 29. So all these phases dropped a lot, and that's because there's a lot more metal missing at the ID surface, and the heavily weighted dense eddy currents at that surface depth, we'll call it, you know, they have a lot of input towards the phase and amplitude signal, so that's why it drops them. Next, we will move up to, that's where we went from the one hole to the two holes, and the reason you're only getting one signal per frequency is because these two holes, where are they? These two holes, okay, so they're, well, it's averaging the two holes. Now they're offset a little bit, so that's going to make the signal look a little wider on the strip charts, but you're still just getting one signal because there's some overlap there. So on the initial single hole, 20, 18, 21, and on this one right there, 18, 15, 20, so it dropped a little bit as expected. We go to the next one. That's where it's starting to get really gnarly, because that's where we've got three of them. There's three holes there. Okay, so, oh crud. That's what happens when you get jumpy with your fingers. You erase the screen, you got to reacquire the data. But no problem, we can do that. This is the digital instrument, and we can do whatever we want with it. It's in here somewhere. Perhaps, you know what? I lost my way. Oh. Okay. Remember, I changed my span so much that even the largest of signals barely show up on my strip chart. So you might go, oh, that looks like clean data. Well, it's not clean data. It's just data with your span set really, really in the non-sensitive manner. And you're only seeing the big indications on your strip chart. So you got to be careful with your span settings. Okay, so those are the 4 big ones right there on the right end. Remember how bad that end of the tube looks? So the first one, display config, data cursor, no, measure, peak to peak, 18 degrees. Come on now, 18 degrees. And then the next one is what? 20 degrees. Yeah, that's getting to the area where the holes are, they're, maybe drilled at different angles and slightly offset, so the phase differences are going to be acting a little bit wonky. Get a little saturation here in the differential. But now let's go look at the absolute channels, because we haven't looked at those much yet. So there's 2, and then we'll put 4 up here. And I guess I probably have to go and change. See, now my absolute signals are blown way off screen still. And that's not going to work for us, because we need to be able to see the signals, all of the signal. Can we even get that one back on the screen? Whoa, so 45 kilohertz was okay. It's just the high frequency that is a little bit spazzed out from that huge hole. What about channel 6? Is that going to be saturated? Let's bring it down all the way down. Nope, that's the wrong adjustment. I was changing my X to Y ratio, and that's definitely not what we wanted to do. I need to bring that back to where it was. Come on, hula button. So what happens if you change your X to Y ratio? It's like changing vertical gain up and leaving the horizontal gain alone. But if you want to adjust the vertical and horizontal gain in tandem on the MIZ-27, you have to have them set to the same thing, which in this case is 0.7, and then you go adjust the XY. So now when I bring it down, is it going to be good for us? Not saturated. So channel 1 was the only one that was saturated. And if you wanted to fix that, you could go in the hardware config, and you could take this down to 34. Now it claims in the manual that's going to take care of my saturation issue. So there's a null. Hopefully I'm annulled it in the area of good tubing. If you don't, you'll notice it. Okay. So now that we dropped the gain in our config, which is different than changing your spans. Let's go all the way down to there. Okay, so now as I scroll through, none of my absolutes are saturated. None of my differentials are saturated because I already checked that. But now what we're going to do is we're going to basically go look at all of these indications with the absolutes. Maybe I'll leave channel 1 vertical just to help me see where I'm at. I don't have a script here. I'm just kind of going along as I think of what to tell you. So just bear with me, be a little patient. There'll be a lesson buried in here somewhere. Okay, let's see, data cursor. So now we're going to move on down to the 100% hole, 0.052 inch in diameter, which is right there. And then we're going to change the spans, make it a little hotter, so we can bring the absolutes on screen. I'm going to have to make this window size a little bit bigger. Right there. Okay, there's channel 1. Or channel 2, I mean. Channel 4, we need to pump up the volume on the span. There we go. Same thing here. And finally, channel 7, 10 kilohertz. pump up the volume. Oh, I need to be channel 8. See? Okay, that could probably be a little bit higher if I wanted to get exactly perfect for you guys. It's not about perfection. This is about teaching a lesson. So what we want to do here is let's just note the phase of this signal. Of course, when you're doing absolutes, you want to get on the leading edge. You want to get on the leading edge, which is that right there. That's what you want to measure. So we're going to go peak to peak. All right, 39 degrees. I know how much you guys like perfection. So we're going to make sure that this one is, you know, I could set noise horizontal, which I think is what I initially did. But if you really want to see the effects of making the holes bigger, it'll probably make more sense if we've got the rotation of these things set to 40, just a better number for you to remember. All right, just about 40 on all of them. Now, we're going to go up to the next big 100%er, which is right there on our strip chart. Remember, because what we had was, if you look on the strip chart, 420s, 60, that's the 100 we were just playing around with, that's at 40 degrees. Then we got a series of flat bottom holes from the OD. Then we've got a big 100%er right there. And if you get on the leading edge of that signal, my guess is it's going to be less than 40 degrees. What do you guys think? Well, obviously I didn't grab the leading edge. I grabbed the trailing edge, see? But at least I'm smart enough to know what I did. That's a good thing. So I need to make that window a little bit smaller. And then I need to make sure I'm on the leading edge, which is right there. So I'm still saying we're going to be less than 40 degrees. 35, 34, 31, 34. So the theory holds true. Because more eddy currents are disturbed at the ID surface where the eddy currents are the most dense, you know, that's going to provide a lot of input to the signal phase and amplitude. It's going to drop it down towards the horizontal or the surface phase, which is in theory 0. Now we're going to go to the next series of flat bottom holes. So that's going to be, let's see here. Our first hole was right there on the left. Then our second big hole was this one. Second. So this is going to be the next hole we look at, which is right here. But first, let's remember what the phase of this one was. It was like 35, 34, 32. All right. 35, 34, 32. And then when you go to the next bigger hole here, that's probably going to be your phase angle there of the absolute. So let's go to measure peak to peak 27, 25, 29. Can you see a pattern? Hopefully so. Now we've got, this is basically the last set of flat bottom holes leading up to a large single through wall hole. So as you can see the phase, that's all OD. Those things, the signals are rotating counterclockwise with decreasing frequency, just like they did on the differential channels. But now when you get up to that big 100% hole, which is right there, that's not the leading edge, Eduardo. Gotta get a little bit farther down on it. It'll help if I span in a little bit. It's going to be right there. And again, these things are blown off screen so much that I probably need to span them down a little bit to see, to make sure that I'm on the leading edge of the signal. So taming down my spans a little bit will help. So I'm scrolling up into the 100%er, and that's the leading edge of the signal right there. So to measure it, 28, 26, 29. And again, we're getting back into the point here where, depending on how I drill my holes, my drill bit may not be going straight down. It might be a little bit of an angle. There's some burrs and some material left on here. And especially when I get into where I'm doing multiple holes, they're actually offset a little bit. The inclination angle of the drill bit's probably a little bit off. So your phasers are going to mess around a little bit. But, if you look at the Lissajous screen, what you should see is a great big differential signal confirmed by a great big absolute signal. So you got to use the totality of all of the information that you have on your test instrument. And then what do we got on the other end here? That's where we got all this big, the real big nasty holes. So let's go see here. One. So yeah, that was right here was the first big hole. I don't know if I said that right or not. Hold on one moment. I have to get my coordinates here. I got to get my bearings right. That's a differential signal. Okay. So we're going to change it to absolute. Which one's that? That's the green one there. Let's hit null, bring him back on screen a little bit. The purple guy needs to get back on screen a little more to make some more sense of it. And we're going to tame down 10 kilohertz a little bit. And while we're at it, we're going to go tame down 45 kilohertz a bit too. Boop, 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 boop. All right. Null, bring everything back on screen. So here we have 20, 17, 21 degrees. That's the single big hole, the biggest drill bit that I had. And then we go up into the one where there's multiple. So it's basically twice the amount of metal missing. And hopefully that's the leading edge there. And 19, 16, 22. It's still dropping, right? So that's 2 holes. Then we go to 3, where we got the 3 holes. Obviously, that's not the leading edge. So hold on a minute. There's first hole, 2 hole, 3 holes. And if you look at the strip chart, you can even tell that it's a little bit more axial distance or time. So that's because I don't have the drills holes set exactly right around the circumference. Measure peak to peak, still not on the leading edge. It's hard to tell because these things are all blowing way off screen, so I have to tame them down a little bit yet. The reason they're blowing off screen is because there's so much metal missing, length times width times depth. So it's making our signal blow off the screen. That's why they do that. So now, let's see here. I want to make sure I get on the leading edge, which is right about there. And then I'm going to hit measure peak to peak, 22 degrees, 15, 18. Okay, so let me get to the very, very, very last one. This is where we're running out of tube over here. I mean, it's mostly holes. That's what that signal is. So to get that on screen, I'm to the point now again where I can't even get it on the screen. So I would have to go drop my gain and my config even more to bring these signals back on the screen. How about a lower frequency? Let's see if we can bring that one on the screen. And then we're going to go over here. We're going to bring this one back on a little bit. And then the final part of this little exercise, we're going to take note of something. Okay. I'm trying to null to get the, that's probably good right there. Okay, so let's take a look at the 100% hole That's 0.052 inches in diameter. Can you even see it? Not really. But that's all the big 100%ers. And you got the peak to peak. No, it's not right. You got your peak to peak. That's not right yet. You got your peak to peak, 25, 18, 20. What you're getting here is a little bit of almost like edge effect, because you're, edge effect is usually on like plate. When you're getting the coil really close to the edge, you'll start to see the impedance change, and it'll go more sort of in the same general direction as an unloaded coil or air, the air point. And when you're dealing with bobbin tubes or inside coils or external feed-through coils, called encircling coils, then you get a thing called end effect. It's the same effect as edge effect, but it's referred to as end effect because you're reaching the end of the product. And it goes in the same general trajectory as air. So as you scroll up into that big mangled area of tubing, your impedance shoots way up to the left. Same direction as flaws, right? But let's watch what happens when we go to the actual tube end. It looks just like that big, huge set of holes we had at the end, except they're going to be even bigger because there's a whole lot more metal missing. All of it, right? And just to confirm this, let's just go and measure the voltage of the tube end. 41 volts on channel 2. And then if we go to that last really big hole here. Hold on. So we're going from 42 volts at the tube end. And when I hit peak to peak on channel 2 there, it's going to be less than 42 volts. You wait and see. 37 volts. So, I mean, it's still a very large amplitude signal, 37 volts. But when you went out the end of the tube and saw air, that's the ultimately bad situation. All the metal's gone. Your probe's hanging out there in air somewhere. And, that gave you the much larger signal at the tube end signal. And actually, they use the absolute voltage signal, a tube end signal, to turn off the probe pusher so you don't mangle your probes when you're collecting a lot of tubing data at high speeds. So I hope you enjoyed this video. Thanks for having patience as I worked through all the different channels and phases and rotations. But if you have any questions on this video or you have comments for another video, just leave a comment below, make suggestions for new videos, like and subscribe if you find this material beneficial and helpful, and subscribe to my channel and go to eddycurrent.com. All right. Have a nice day.